So we just looked at this so-called data-driven approach. Why do we resort to using data to create algorithms, especially when problems seem to be difficult to be hand-coded? When you, for example, were trying to write an algorithm to recognize these hand-coded digits 2, it was very quickly becoming very complicated. But when we resorted to data, we simply asked people to write these handwritten digits 2, and then we took an average, and then the problem became way simpler. So in such cases of the family of problems where we can use data, how do we do these data-driven approach? So the common thing, the common way of doing this is to start with a data set, especially in the so-called supervised approach. We start with a data set of, say, images and their corresponding labels. They need not be images, they can be a row in a database, they can be a speech segment, they can be a text block. But this is an example because we did a handwritten digit 2. Let's just say we have images and their corresponding labels. And in our case, we happen to have images of, say, cats, we have images of dogs, and we have images of, say, mugs. Yes, and what we want to do is we want to use machine learning to so-called train an image classifier. What does it mean? It means that after we have the trained model, like our average model, which was without any learnable parameters, we will then be able to use this model and then predict what the input image was. We may be able to predict, okay, given an image, is it an handwritten digits 2? Or is it a cat, or is it a mug? And what we do is we start by creating these two functions. We start with a train function and we start with a predict function. So what do we do in the train function? We give it images from our training set, the ones that we just created and labeled, and we also pass the corresponding labels. And what does this train function give as output? It returns to us the trained model. Now the trained model can be very simple. It can just be that average image of 2 that we spoke about, or it can be our nearest neighbor classifier, which we will look next. But what we should remember is that we have a train function, and the train function gives us the trained model. And then of course, once we have the trained model, we want to use it in the predict function. And what does the predict function do? It takes in your trained model from here. It also has these test images that we give as input, the images that we are interested in real life. And this predict function gives us the labels for our input, which we do not know the label for, right? So if we give it a digit looking like this, it should say it is a handwritten digit 1. If we give it an image of our cat, it should be able to return that it's a cat, and so on. So this is essentially the data-driven paradigm, where we use, where we start with a data set of, let's say, our data and their corresponding labels. We then use machine learning to train a classifier, a regressor, a model of any kind, and then we evaluate that model on a so-called withheld set, the test set. Yeah. So we will understand this in a lot more detail. We will talk about validation set, cross validation, and so on. But for now, let's just remember the example that we looked at. We had a larger set of handwritten digits 2 for our training, and then we had a few images which is usually smaller than our training set for testing. So this is our test set and this is our training set. Okay. So now here we will train a very simple classifier for, so this is a little bit more complicated, let's say, than our handwritten digit example, because that was just the average of all images. But here we will train a so-called nearest neighbor classifier. And the nearest neighbor classifier is dead simple. All we do is essentially remember our training set. And we will do this as a take-home assignment, and then we will discuss this in our office hours with the TAs, and then we will also talk about it in our live session with me. But And here I have written this in Lua because then you get a chance to write it with Python using NumPy, right? But here, just so that we, kind of understand, so think of this as pseudocode. You don't really need to understand the syntax, but what we are doing is we are creating these two functions, the train function and the predict function. And to the train function, what are we doing? We are giving it our entire data set X and our labels Y. And all we are doing is we are saving it in our state variables, right? self.tr_x, self.tr_y. So all we are doing is we are doing something very lazy and inefficient because we are storing the entire data set and we are calling this in some sense our model. We'll see how. Then our predict function is also very simple. Yeah. What we do is we then loop over our entire data set that we have saved in our self.tr_x. So we go from 1 to the length of the data set, and for every data point in our data set, we compare it with the interesting data point that we are in, right? So we are passing X as input and we want to find which, let's say in this case, image in our training set is closest to the test case that we are interested in. So we want to find a label for X, we give it as input, and then we go over the entire data set here, and for every image in our data set, we try to find this so-called absolute distance. And absolute distance is something very simple. So this is, let's say, a small 3x3 image. Though in reality, if we do our handwritten digit, they are 28x28. We will look at a data set called CFAR. So then it's 32x32. But here, for explanation, let's say this is, our images are of size 3x3. Yeah, and this L2 distance, all it means is I want to take whatever is my value here, let's say 4. And whatever is my value 3, and I want to subtract it. So it's 4 minus 3, and let's say my output is all here. So I want to subtract 4 minus 3 and write it as 1. But now suppose I have 2 here and I have 9 here. So 2 minus 9 is minus 7, but then I take the absolute and I write 7, right? And then I finally sum it up. So L2 distance can formally be written as sum of all my distances, right? So sum of everything, I will loop over all my images. So A of, let's say, ij from my training set, and we have another, let's say, x of ij, which is our test image, and we want to kind of compute this for each pixel. So we will have like a double loop here if we want to, but here we are vectorizing it, and so will you using NumPy, and then we will sum it up. So this is what it says: the absolute sum of all these point wise, all these components of the images, in this case the intensity values of the pixel, we just subtract it one by one. We have subtracted image, and then we take the absolute of it, and then we sum it up. So finally our distance will be one scalar number, a single number. Mathematically, when we write scalars, we say it belongs to this so-called set of real numbers, R. When we, so this is a one-dimensional, R to the power 1. So this is how you write it formally. Though it's not important, all you should remember is, this is just a scalar. A scalar means it's a single number. It's not a vector. It's not a vector which has, let's say, more numbers than 1. It is a single number scalar. And then we are trying to find the smallest image, smallest distance. So we are looping over our entire data set, and we were trying to find an image in our data set which has the smallest distance with this image x that we have passed in, right? So we are trying to find the image in our data set which has the minimum distance with the image that we passed. And once we find that, once we have gone over the entire data set, once we find that image, we just say, oh, the label of this image that we have passed in is the same as the label of the image for which we already have labels in our data set with which we had the smallest distance. And this is what we are doing. So we are trying to find the distance, and if the distance is less than minimum distance, we save the minimum distance as the current distance, and we also remember the index of that minimum distance. And finally, as label, we just return the label so our training set labels, we just return the index that had the minimum distance, the min IDX that we saved here. Yeah. But in reality, this has problems. This nearest neighbor classifier has problems. Why? Because test time performance, which is usually more important, here is dependent on our training set size, and it's very inefficient because we are looping through our entire data set to find the right label. And machine learning flips it, right? Be it CNNs, be it transformers and so on, which we will look at later. Our machine learning models, even the linear classifier that we look at next, completely flips it. So the classification speed doesn't depend on the training data sites linearly, it is much faster. Right, so nearest neighbor may work, but it's super inefficient. So it is a good way to kind of start thinking about it. It has certain advantages. Maybe in real life you might want to use a nearest neighbor classifier, but usually we don't use it, and we use other techniques which we will look at next.